Hello, everyone. Thank you all for attending this presentation of our multifaceted case study of 3D metal printing. We're really glad you're here, and we're really excited to show you what we've discovered and what we've developed. Next slide. Additive manufacturing is on the cusp of creating a revolution in manufacturing. It provides a way of potentially making parts faster, cheaper, more complex, and even more effective than what was previously thought possible. However, because this technology is relatively new, there is not much data yet established on the material properties of 3D printed materials, as well as in many other aspects of 3D printing process. Our project was aimed at tackling some of the biggest unknowns in this area of engineering. Next slide.
Our project had three main goals. Our first goal was to design a part using additive manufacturing techniques, which can then be compared to a conventionally manufactured part. Our second goal was to perform material testing. Of particular interest was fatigue testing on coupons which have not been surface finished. Our third goal was to develop a method to detect errors which occur during the recoding phase of printing. Next slide, please. For prototyping, we utilize finite element analysis to minimize the amount of material in the design. For testing, we tested fatigue strength of unfinished coupons, tensile strength at high and low temperatures, and surface roughness. We also developed code to detect errors in the recoding phase of the print. Next slide, please.
So material testing. Next slide. So given our design requirements, we determined that we had four main testing objectives. The first one, to determine if the 3D printed aluminum meets the strength requirements throughout the anticipated operating temperatures. Two, to determine if surface finish machining is necessary in order to preserve part integrity. Three, to determine natural resonance frequency of the final part, where it's greater than 20 Hertz. And finally, to develop an automated printed error detection program to determine whether printed parts have any hidden errors without having to perform destructive testing. Next slide. We performed extensive tensile testing at 150 degrees Celsius and negative 20 degrees Celsius to simulate the potential environmental conditions these parts would be operating in. We did this in order to determine the ultimate strength, yield strength, and failure strength of the printed parts at these extreme temperatures. These results were then used in the finite element analysis of our part to determine if the parts themselves would withstand these extreme temperatures without failing. We were able to conclusively determine that the final iteration of our part will withstand the heat forces it will be exposed to over the wide range of environmental temperatures if it's expected to operate in. Next slide.
As printed surface coupons were tested on a MTS machine, the frequency of the machine was set to 10 Hertz. And in testing the aluminum 660 coupons, tests showed that as the ultimate stress force decreased, the cycles increased. Tests were decreased at a rate of 5% UTS per test, and results fell within a reasonable curve that are similar to non-3D printed manufactured aluminum. Next slide, please. Then a resonating test was to determine the frequency of the part. A specification of 20 Hertz was given to us by Lockheed Martin to ensure the integrity of the part would not vibrate apart. The test was performed using a PCB Piezotronics impulse hammer set to an instrument of an Elvis 2 board for the data acquisition. The part was then hit with the hammer and the frequency of the part was recorded and data was compiled. And the average resonating frequency resonating through the part was around 910 Hertz, which is well above the given requirements. Next slide, please.
The next major goal of our project was to explore the possibilities of non-destructive print error detection. Next slide, please. The printer has two printing stages. It lays out a new layer of aluminum powder evenly as the material for the next layer of the print. It then exposes the desired area with a high-powered laser to melt the powder and then add the next layer. The printer is extremely accurate when it comes to the laser exposure, so very few of the print errors or print failures occur in that stage. The recoding, on the other hand, has led to aborting prints, and few cases of part failure. Next slide, please. We decided to develop Python scripts that can clean up the images taken of the powder bed from the built-in camera and detect when the recoding is not uniform and likely to cause errors. Next slide, please. The additive team at Lockheed directed us to this print where the top test coupon failed a material test due to recoding. We took these images shown here and developed some custom code using machine vision techniques that filters and reshapes the original powder bed image to one that makes the irregularities in the top coupon much more visible. Next slide, please.
So now that we knew that we could detect some recoding images, we needed to find out how to test the limits of the printer and the built-in camera. So first we designed some more custom code that takes the after laser exposure images and transforms them into images very similar to ones produced by a slice of the original input CAD files. This allows us to see exactly where the parts are for our error detection. We then needed to test the print. We then needed to test the printer limits to see what intentional errors we could later introduce to see what errors we could detect. So we found that the printer has a minimum size of 0.002 inches in diameter to print, and the camera, using our mapping, has about 0.01 inch per pixel, allowing us to know exactly how large of an error we can detect.
All right, here's a quick snapshot of the part itself on how we designed it in the specifications given to us. Next slide. From here, we have a basic height, overall diameter, structure masses, as well as weight that we must stay within. Next slide. We started off with a simple SolidWorks design, pretty bulky, pretty thick of the cone shape itself, and all given masses and internal bulk parts and pieces. It started at about 22 pounds. Next slide. From here, we kept scaling it down, removing material, keep getting it thinner and thinner to the point where it got lighter and lighter. It got to about 6 pounds. Next slide. From here, we were able to get it a very lightweight prototype version to about 4.3 pounds overall. We had a couple redesigns from the prototype phase to get it to where it should be when it comes to strength and our overall factor of safety. But overall, our part printed successfully, and it actually turned out really well. And that's it. Next slide. And here are some quick acknowledgments of everything and everybody we that helped us out, and we sure appreciate it. Thanks a lot, guys.